Good evening, folks, and welcome to this webinar, which is entitled 3D Graphing on TI Nspire. Thank you very much for attending this particular webinar, and I'm sure that the two presenters will offer us some really interesting insights into how we can use the 3D graphing feature of Nspire for good teaching and learning. So first of all, we're going to hear from Brian Lannon. Now, Brian's got a bit of a head cold or man flu, and last night in Melbourne, Peter Hitchener had a coughing fit while reading the National 9 News and couldn't finish the news. Something similar could happen this evening, but we think that Brian will be able to complete his presentation. Brian's taught in Victoria, New South Wales, New York City. He's been a consultant. He's taught for about 150 years. He currently is at Victory Lutheran College. He's going to start proceedings, and following Brian we have Jim Lowe, who I rate very highly as a preeminent authority on STEM in mathematics classrooms here in Australia. He's creative, passionate and articulate, as is Brian, and Jim is also working currently at the Queensland University of Technology. So, without any further ado, I'm going to hand over to Brian, who's going to start this evening's presentation.
Great, thanks, Peter. And of course, everyone's waiting to hear that croak, aren't they? Everyone's happy to hear the croaking voice at the school I'm teaching at. Gradually, the various teachers and students have all succumbed to the winter lurgy. I am holding out. I don't get these things at all. But I did wake up this morning with this croaky throat, so we shall still continue on. I'm hoping now that you may be seeing my desktop. It says something like 3D graphing on TI Nspire, and an overview of the things that we have in an action-packed webinar for you this evening. And if just looking at it isn't enough, this is what it might look like in some pictures. So all very good. We've got quite a few number of people enrolled for this evening's webinar. I don't know if it was the topic of 3D graphing, or whether people just wanted to hear what a croaky voice sounds like. But you didn't know that was coming, though, did you? Now, listen, I've got to admit that, I don't know, about 150 years, Peter, but I have been using the graphics and CAS calculators for over the last 20 years. I have been aware over that time that 3D graphing has been a capability that's been there for most of that time, and now I must admit that I've been actively avoiding it. I've been happily living in a two-dimensional world. Please don't upset me. Why make things more complicated than they really are? I'm very happy with two variables being related by a function, a Cartesian plane. Look, parametric if you really want. That's been good enough for me. But I'm aware that the evidence has been mounting against this whole flat Earth type thing. Look, flat's nice. It goes on a presentation board. You can write it on paper. It fits nicely into a book. But if we do look more to the future, we have our students walking around, living half their life in a three-dimensional computer game environment. Even their televisions are jumping out at them in the third dimension. And this one here, the three-dimensional printing, and that's really over the top. Maybe we really should have a look at this sort of thing. So finally I bit the bullet. Earlier this year I attended a session at the T-Cubed International Conference that was run by another T-Cubed presenter, Stephen Phelps. And look, I was pleasantly surprised. It really wasn't as hard as I thought it was going to be to get started with this. So that's our aim this evening, is to get you started into this. And if you already are started into it, then we're going to take it further and get into some other applications and so mapping of solids of revolution and the like. But let's get the show going. First of all, if you are not already aware, how do we get our calculator into the 3D graphing view? I show you here on this PowerPoint, of which you will get a copy after the webinar. And this is the sort of thing we'll get. Let's have a look at it on the calculator. Now, if you do want to join us on the calculator, what we aim to do this evening is to start you off in some of these constructions. And if you want to start on that, that's fine. But then we will move on and commence another construction. Don't worry, you get a copy of the PowerPoint that has all of the formulas for a construction. And not only that, we will also give you the TNS files. So like me, you could show it to your students and go, ha-ha, that's something that I built. In this case, this actually is something that I built. This was in the session that I attended earlier this year. Okay, but you want to know how to start the show off. Not that one, but this one. How do we get this 3D box appearing? Well, when you add a page, when you add a page, if we add either a graphs or a geometry page, doesn't matter. This is the standard graphs page. If we then go into the menu and change the view to three-dimensional graphing. Now, the same sort of thing, had I added a geometry page, it's the same deal. Menu, view, and 3D graphing. And these two pages, these two tabs are the same. You can see I have the entry line here, which is Cartesian-based. How can I define Z in terms of X and Y? But before we jump into that sort of thing, let's just tab out of that or click down in our space down here and learn how to drive it around a bit. At this point, I will jump back to our PowerPoint just to reassure you that you have this in summary. The letters on the keypad, R will rotate the box, A will set up automatic rotation, O will take you to, well, I call it the original view. You may wish to call it the orthogonal view if you prefer, and X, Y, Z will give you a view looking down each of those positive X axes. You can zoom in or out by pressing the multiplication or, zoom in by pressing the multiplication or right arrow keys, and out with the division or less than keys. Not right arrow, it was the greater than. Let's jump back to the calculator and have a look at this. Obviously, I'm using the software version here. If I want to rotate this around a bit, I just click in the space. You see my four-sided arrow, and I just move this as I wish. Alternatively, if I pressed R on the keypad, you see the little rotate thing pop up. Top left shows me I'm in rotation mode, and sure, I can do that with my software, but at this point you need to be aware that if you're coaching students on this, when they've pressed the R, in order to start to use their touch screen on the keypad, to activate that, they would need to click on the clicker in the center of the touchpad, which will effectively bring up that four-sided arrow. And once that's happened, it activates the touchpad so they can swivel their model around. That one's fairly boring, but hey, isn't this one nice? And just to give you an idea, O for the original view. A is a nice one because that sets the whole show in motion. I think there should be some sort of soundtrack to that. It would sound very technical when we're tuning in. Maybe the theme from the dish, possibly. I don't know. But we're rotating our model around the Z-axis. And I can escape to stop that happening. Press X to have a look at things from the positive X-axis point of view, or Y Z, and isn't that a lot of fun? And as I said before, we can also zoom in or out. And let's now get going with building some of these things. First thing I'm going to challenge you to build is a box. Why not? Boxes are useful. You know, you can keep things in them, stack them on top of each other, whatever you like. Let's go back and let's go to our plane here, and let's go to, I'll escape out of my rotation mode, tab for entry, and okay, Z's being defined in terms of X and Y. Let's make all Z values equal 5. Why not? I can kind of see what's happened there, and it makes sense what's happened as well. I've kind of put a roof on my box, and I'm pretty confident that you people watching will be smart enough how I could put a floor on my box. And I'm going to, well, okay, well, let's just jump that in. So we'll put in -5, whoops. And there's the floor to our box. What about the sides? That gets a little bit more difficult because you'll have noticed that I've got Z defined in terms of X and Y. I don't have the others defined, like, for example, X in terms of Z and Y. So I employed a trick here where I thought, let's make a plane that's vertical, or pretty close to vertical. Let's make Z equal 1,000 X. Now, 1,000's a reasonable sort of gradient, and I know it's not totally vertical, but, pretty much looks it, don't you think? It's in the wrong place. Okay, let's go up and change that. I know how to do translations, so let's make this, shall we go X -5, and that'll move it across to the right 5 units. Oops. Okay, it's moved it across. I'm reasonably happy, but hello, I'm missing half of it. And the first time I did this, I thought, what's gone wrong? But think about what we did. This black panel, so to speak, was built by a plane that has a gradient of 1,000. And what's happening is we're seeing it below the XY plane, whereas higher than the XY plane, the panel still exists, but we're not seeing it inside our 5 by 5 by 5 box. A range of ways we could possibly fix that problem, and I thought, let's keep it simple. I already confessed that I like it simple. So let's just do the negative of the same thing, and there we go. Although you may have noticed, because I've now put a fourth function defined here, it's now come out in a fourth colour. So let's change the attributes of this. So a right click, or if you're using the handheld, control menu, and you'll see the menu here is colour. And I want to change the colour of the fill to black, and woohoo, we're on our way. So if you've followed along and built that so far, that's looking good. Don't worry about building the rest of it now, because in the PowerPoint you do have all the answers. But you're going to do better by thinking it through. How do I build each of those panels? All good fun and a lovely challenging problem for students and getting them to look and view things in 3 dimensions. Here's the next one I played with. This was the last school holidays. I mean, you sit around at your holiday place and play with the computer and see what you can make. Now, first of all, can I point out that I've just called this thing a star. I'm quite aware that there's probably someone tuned in that will have a far more mathematical name for it. I don't care. I'm calling it a star. And let's look at how we start building that. Well, the first panel, you saw what happened when z equaled 5. Let's make z equal 0. Okay. But I don't think anyone's too surprised to see that. And the vertical panel, let's go with z equals, shall we call it 1000x. We sort of saw something like that before. This is looking reasonable so far. But how do I get the one that comes across here? Bit of fooling around, and there's nothing wrong with just exploring and seeing what happens. But how about 1000x added to 1000y? Well, oh, hang on, I've got that on the angle. Sorry, 1000x was what I was just looking to do. Getting ahead of myself here. 1000x we have done, sorry. 1000y at this point. I've given you away the next bit too early, haven't I? So here we have this, which looks nice so far. And you might want to think of how we can get some of the oblique ones in and graphing things such as just z equals x. And I'll let you to work on that to think about how we can put all of the rest of those panels in. But you remember, if this is what we're trying to build finally, this one looks like it's gone through a bit of a soft lens focus or soft focus. We don't have all this gritty type stuff sitting around. So once again, let's go back to attributes. And on this, if I highlight something with a right click or a control menu, the attributes of that panel, you see in the first option here, it's showing the surface and wire, so to speak, as if the thing was made out of a cross-section or grid of wire. My options are to show the surface only, which is what I've done in my earlier model, or I could show just wire only. I'm going to go with surface only. And I could do that to each of my planes and sort of make it look all nice and pretty. But you may recall that we didn't have the box here, we didn't have the numbers, we didn't have the axes, we didn't have the legend up here. There's a range of ways of hiding those. I thought the easiest might be just to go into the menu and then view, and I can choose exactly what I do or don't want to view. For example, let's hide the box. Box is gone. Go back into that. Let's hide the legend up in the top right. That's now gone, and so forth. Okay. And again, in your PowerPoint, you've got the answers to all of these, and if you have difficulty working through the PowerPoint, we'll send you the file as well. Next challenge for you, consider the cube that we've got and what cross-sections we might have when I run a plane through a cube, which is a 5 by 5 by 5 cube, and I'm only seeing the part of the plane that intersects with the cube. Can I make a hexagon? And this looks a little bit like an equilateral triangle. Well, yes, we can, and I'll give you these ones. Just adding x and y will give me the hexagon. Try it on your handheld. And the equilateral triangle, I've actually taken that same hexagon and moved it. And what's happened is it's got pushed out of the box to the point that I'm only seeing the equilateral triangle. That's a neat one, and one that kids like to have a bit of a play with. So here we have our hexagon. Here's our equilateral triangle. I know you know how to build a square, and I know you're also smart enough to know that if I put the square on an angle, I'm going to end up with a rectangle. What other cross sections are there? So that's all good fun with Cartesian input, but it really, life becomes a lot more interesting when we start to play with parametric input. And I'm going to try and build a sphere. But I told you before that I do think of things in a fairly simple way, and I did prefer the two-dimensional thing. Let's just start with a circle, which we know looks a bit like this. And so if I input x squared plus y squared equals, say, 25, I would get that circle there. But I could also do it in parametric, and we know that the parametric equations for the same circle. At this point, let's consider how we switch the thing into parametric mode. In your menu under view, if we go into 3D graph entry edit, we have the options of function or parametric. So the function was the bit that you've already seen, where Z is defined in terms of X and Y. Parametric is when we define X, each of X, Y, and Z in terms of angular variables. I'll just show you on the calculator how we set that up. Let's go back to our document, and let's go for, I'll put in a new problem just to make it all nice and tidy. And here we have our 3D graphing view. Of course, the circle, first of all, in Cartesian, x squared and y squared equaling 25. Perhaps I've done something a bit strange there, haven't I? I need to first of all put that into parametric. I looked at the Cartesian version, but I do need to put this into parametric for this, because obviously the circle isn't a function, is it? So in parametric terms, and I've now converted my x squared plus y squared equals 25 into the circle. If I go with r cos t, where my r is 5, by cos of t, and at this point, avoid tab and avoid enter. We're actually better off arrowing down, and 5 sine t and because I'm liking things flat, I'm just going to go with 0 for the z, keep it simple. And so here's my flatland circle. Now let's try and have a crack at this third dimension. If I put down into the z land, t of course being the angle that was made between the positive x-axis and the radius that connects our point from the origin, I'm going to put another angle into the game. Let's go with cosine of u. It's not you, it's me. No, it's me, it's you. Where u is the angle that lifts us up off that xy plane. And let's just see what happens. Oh, okay. I've now got that third dimension happening, but it's not very big. I can see what's happening. It's oscillating between -1 and 1, which is kind of what I thought might happen with cosine. But if I pump this up by a factor of 5, woohoo, now we're talking. Still not quite a sphere, but I do like it. We don't necessarily have to reinvent the wheel with everything, but I do like it. It's nice. Let's get out of that. Let's jump back up here, and let's see if we can finally get this thing looking spherical. I said it's not me, it's you. Let's go with multiplying each of these by sine of u. And once again, the sine of u. And let's see what happens. I need to arrow down to get out of that. And let's give it a go. I've done something that it doesn't like.
Brian, did you use the multiplication sign in the Y?
No.
Oh, I've hit the dot on my keyboard. Thanks there, Flemmy. I'll go back to my calculator. That's safe. There we go. And so there we have it. Thanks, Peter. So there we have our lovely sphere, which is probably even worth zooming in on. And yeah, you could imagine that as planet Earth. You can see me here in Yakandanda. I'm down about here, at the top of 10 degrees today. But meanwhile, I'm up about here somewhere, sitting in the warm sunshine, is Jim Lowe. So, Jim, I think that's probably a nice segue to hand across to you. If he hasn't run away on us.
Work out what's going on here. There was a little bit of a lag there, and I was still seeing a cylinder when you were talking about a sphere, and all of a sudden it came good right at the end, just before you handed over.
No excuses. We know that Queensland are a bit behind in daylight savings time, but you should be on the ball now.
And the other mess is I've been up in Toowoomba today, and it's anything but warm. It was bright sunshine, but it was freezing. Anyway, I'm going to carry on from where Brian left there and talk about solids of revolution. And we're going to achieve our construction of those solids of revolution by using the parametric equations that Brian introduced just there. So let's have a look at this, and we're going to do a couple of things. We're going to look at a rotation around the x-axis, around the y-axis. We're going to have a look at a region between two curves, and finally I'm going to get a little bit creative with some sliders that we can use to help kids see what's going on in this process. So let's talk about the parametric equations, and let's summarise the process first of all before we actually get in and do one. And for those that would like to get a copy of these files and start playing around, there's a link there to a Dropbox file where you'll get a zip file with the 4 TNS files that I'm working with tonight. So if you want to make a note of that, I'll leave it there for a few seconds while you might want to copy that. The thing that we're doing here with the solids of revolution is trying to build on what the students are familiar with and then take it into the third dimension. So we're going to use the procedure that's outlined there to create these solids. We're going to define the function, first of all, in the 2D world that Brian was very, very comfortable in up until earlier this year when he moved into the third dimension. We're then going to transfer that 2D function into the 3D grid and then define our X, Y, and Z in components in 3D to give us the solid of revolution, and if necessary we're going to edit the limits for the parameters T and U. And that's one of the things I'd like to point out. Brian was describing how he constructed that sphere and how he interpreted T as rotation around or rotation around the Z-axis and the XY plane, and U as a rotation in a direction perpendicular to that. But it's important that you realise that T and U can be defined and interpreted however you like it. There's nothing fixed about T and U, as we shall see. So let's get into it and have a look at it, and then I'm going to come back and, well, let's just look one more slide first. So we're going to look at this solid, or build a solid based on the curve -x squared minus 4. And so that's the first thing that we're going to do, is enter that function into F1, function number 1, in the 2D graphics window that we are already familiar with, and then replicate that in the 3D window, as you can see. So instead of X, our X coordinate is simply going to be T, and our Y value is F1 that is already defined, but instead of F1 of X, it's going to be F1 of T. And as Brian did for his sphere to start with, we're sticking to 2 dimensions, and so our Z coordinate is simply 0. So let's go and have a look at that in the Nspire and look at how we set that up. So rotation about the X-axis, there's our first thing. It's exactly what I said in that summary slide. We've just gone in to F1 of X and defined our function. Having defined the function, we move into the 3D window, and I'm not going to reiterate what we said before, but remember, to create the 3D window, we would look for the 3D graphing and then change it to entry by parametrics. And I'm just going to get out of that there. And there's a couple of little things that we have to do here, but I'm just going to reiterate on a couple of things that Brian introduced. So you can see I can rotate this thing around and look at it from different angles, but one of the good things to be able to do, if I just type Z, then I'm looking along the positive Z-axis. So in other words, I'm looking at the XY plane as we are familiar with. If I type X, I don't see much because I'm looking along the positive X-axis and I can just see a line there. If I look at Y, I see even less. So let's go back to the Z and look along the Z-axis and see our curve in the XY plane. Now, one of the things that we can do is go up here and have a look. There's the function as I've got it defined there. Okay, I said our X coordinate is going to be T, and our Y coordinate is our previously defined F1 of T, and our Z coordinate is 0. One of the things that we haven't looked at yet is this little box over here that allows us to edit the parameters. And if I click on that, you'll see that I've actually changed this. T will default from 0 to 2 pi, and U will default from 0 to pi. I've changed this to 0 to 4, because I'm only interested in that portion of the graph that lies above the x-axis, and it cuts the axis at 4, so I define t to be from 0 to 4. And once we're happy with that, we get out of that, have a look at the graph, and that's why I'm seeing what I see there. If I changed the value of t and made it larger, I would get a portion of the graph below the curve, below the x-axis. So that's the first step that we've got to do, and that's pretty familiar to the students. We're just redefining our function. Instead of f1 of x, it's now a function in terms of t, and our x-coordinate is t. So how did we produce this? How do we produce this solid that we've rotated around the x-axis? And again, we can view it by pressing X, and we can have a look and see that it's been rotated around there. We can look along the y-axis and see that we've got that, or look along the z-axis and it looks pretty much the same. What we've done to achieve that is, well, and I've slipped back into, that's one thing you've got to be aware of, that it defaults back into the Cartesian equation, so you've got to keep going back into the parametric so that you can see your function. So one of the things that you have to discuss with the students in order to do this is that if we're going to rotate it around the x-axis, then the x-coordinate is going to stay constant for any particular point. It's going to rotate and effectively describe a circle around the x-axis, and the x-coordinate is not going to change. So in our previous example, where we had it just in 2 dimensions, the x-coordinate was just t. But now it's going to rotate around, and we need to go back into our components and use our sine and cos functions to get the appropriate components. And so we look at that and we have to make a decision. Why is it that the y-coordinate is the cosine of the parameter u, and why do we make the z-coordinate f1 of t times the sine of the parameter u? And the best way I find of explaining that to students is to simply say that what we need to do is to look at our original thing that we defined in the xy plane, and there with our z coordinate of 0. And so that's what we want to have happen when our parameter u is 0. So if u is 0, then when we have the cosine of u, cos of 0 is 1, so we'll get f1 of t, which is what we had in that previous function. And when u is 0, sine of 0 is 0, so this whole thing will be 0, and so that will map back to what we had in that first function, a graph solely in the xy plane. And so that tells you how to set it up, and there you go, you've got it rotated around the x-axis. And by doing it this way, what we've got is we've actually generalized the procedure for students, because we could go back to our 2-dimensional graphing screen and change this function, and our solid of revolution would automatically change. We don't have to do any more with that. Hopefully that's making sense to people and you've been able to follow what's going on there, but as we said, you do have the PowerPoint, and that whole procedure is summarized there for you. It's actually very elaborate PowerPoint that if I made it live, it would define the stages. So yeah, enter the thing in parametric mode as if it was a 2-dimensional function with z equal to 0, f1 is in terms of t, not x. x-coordinate doesn't change during the rotation, so x1 of P is just T. The y-coordinate becomes the cosine of U, the coordinate, or the Z parametric function becomes F1 times the sine of U, and we do that so that when U equals 0, it maps back into that original 2D function. And that's essentially the procedure. We change our parameters in order to get the complete rotation, and you'll notice that, as I said, the U parameter defaults to minimum of 0 and a maximum of pi. You need to change it to 2 pi to get the complete rotation, and then you end up with your solid of revolution. Okay, let's move a little bit more quickly through a rotation through the y-axis and get out of that again and go back to our Nspire and have a look at, and I've given my stunning endpoint there because I was playing around while Brian was talking before. Okay, rotation about the y-axis, and we've got a slightly different function, but you can see where this one's coming from. This is one of the solids that Brian featured at the early part of the broadcast when he was demonstrating the ability to rotate. So this time we've got x squared minus 4x plus 4 just to get it above the x-axis, and we're still going to rotate this region, the region from 0 to 4. The procedure is very, very similar, but this time if we're rotating around the y-axis, then it's the y-coordinate that is going to stay constant throughout the rotation. And so we need to play around with the x and the z coordinates. So there's our setup in 2 dimensions, or on the xy plane, but within our 3-dimensional grid. And just demonstrating that one again, and notice it drops back to the Cartesian, so we need to keep going back to the parametric, and it's the same as before. The x-coordinate is t, and f1 of t is the y-coordinate. So as we rotate it, f1 of t is going to stay the same, and we need to get the components of this value t. And again, we're going to introduce sine and cosine of u so that when u equals 0, we've essentially got what's on the screen before you there at the moment. And you can see that in this case, if I go to the second function, t cos u, again, when u equals 0, cos u is 1, so we will get t. We'll get our x-coordinate of t, and we put in a t for the z-coordinate. Sine u, when sine u is 0, sine 0 is 0, and so that disappears, and we've got the situation that we've got shown in here. And if we move to the next screen, then you will see there's that solid, simply coloured red, not the pretty colours that Brian had, multicolours, and I haven't quite worked out how to get the multicolours, Brian, so that's something we can talk about afterwards and so on. But again, moving it around, we can do that sort of thing. And as we said, you've now got a generalised file that will graph any function that you put into f1 of x and rotate it around the y-axis. So our generalized procedure there for rotations around the y-axis then becomes something like this, and I won't do the animated version, but enter it in the 2 dimensions over here in the xy plane with the z-coordinate 0. The y-coordinate doesn't change during the rotation, so that stays as f1 of t, and we need the components of t such that when u is 0, it reverts back to this, and that will give us our rotation, provided we edit the parameters t and u to the desired limits that we're looking for. So you can see that once you've got that, then we can go in there and start to have a little bit of fun. And I put this one in here, and you play with a function like 1 over x, and same deal, get the same result there. You can see I've got rid of the grid so that we can see the function there. We've got that, and have a look at the function there, and again it's parametric, and you can see it's exactly the same in as we had in the previous problem where we had the quadratic. The only difference is that in that previous page we've changed our definition of f1 of x in the two-dimensional graphing view. So that's something that you can look at and have some fun with. And when I saw this, I thought, well, I think a lot of teachers would be familiar with an assignment that students get fairly early on in the senior maths in year 11 or somewhere, where they're given the assignment of graphing a series of functions and specifying the domain of those functions such that we only graph particular parts, put a few of them together, and we come up with a cross-section of a wine glass or a vase or something similar. And it's a fairly common assignment. So why couldn't they do the same using this and actually get a 3D view of the vessel that they have created? And so that's what I very quickly this evening, after I got back from Toowoomba, threw this one together, just playing around with that 1 over x function to shift it around and get it to the area I wanted, and then totally unoriginal, just stuck a quadratic on the top and found my boundaries for the parameters, and then just rotate each one of those functions, and we end up with something like that. I think that is a classic wine glass that I actually should be able to bring to market and retire on the profits. I probably am dreaming. One of the things that you might notice there is that I have altered the range. If you look along the z-axis there, you'll see that I've actually shifted the size of the grid, so it now goes from -3 to 7 rather than from -5 to +5. And we can do that in the same as you would in a 2D graph. Go to range zoom and change the settings and just work your way through X max, Y max, and if you scroll down and desire, you can change the Z values and so forth, so that you can get yourself a little bit of room to work with the function. So I thought that's something that students could have some fun with. It just takes it to that, should I say, extra dimension to that fairly traditional assignment, so they can actually see the three-dimensional view of the object that they have created from their functions. Couple of other things to look at here. If we wanted to look at rotating the area between two curves, not going to spend a lot of time on this one because you define the two curves. So let's take that region between the quadratic here and the straight line, and we need to find the points of intersection. So we've got x equals 1 and x equals 4 there, and go to the graph, enter both of them. So you can see here that we've got in the parametric view, x, or the first parametric function is f1 of x, which was our curve, and the second one, I mean, it looks exactly the same because the functions are all defined in the 2D graphics view, and I'll just go back to that again because you will see what I was talking about when I go to the settings here. Okay, previously it was going from 0 to 4. Now I've set it from 1 to 4 because that's the points of intersection of the two curves, and still going to let that go from 0 to 2 pi, and okay, I'm happy with that. So we've got that one there, and you simply, to get the region rotated, rotate one curve and then the other between those, and there's our just the region, just the intersection between the two curves, and we've got that thing to look at. And again, if you look at the equations and go to parametric, have a look there, again, it's that generalized view that we've got of the rotation. So it's rotation about the y, so the y coordinate doesn't change. We get the components of this value t, and we set it up so that we get the two-dimensional view when t equals 0, and our second function looks exactly the same. The key thing to do there is to have the parameter values set, or the intersection between the two curves. So that's, once you've done the first ones, that's a relatively simple one to set up. Okay, what I wanted to quickly do in the last 5 or 6 minutes of this broadcast is to look at using sliders to control the rotation. And why would you want to introduce some sliders to control the rotation? Purely from a teaching point of view. So you want to illustrate to students what's going on with this. We've defined our function here as before, and we've put it into parametric form, and I've created a slider which I've called turn. And turn goes from 0 to 1, and as I move that, I will get a complete rotation. As you can see, it starts to build a rotation, and we can take it all the way around, and my mouse is sliding on what I've got on the bench top here, and if I take it back, then the good thing, I'm rotating this around the x-axis. So if I press X, whoops, keep remembering to get away from the slider. If I press X, now I'm looking along the x-axis, and you can start to see this thing rotate around the x-axis, because when it's at 0, the curve is lying in the xy plane, which is the horizontal plane facing us at the moment, and we start to rotate it around and get a complete rotation. And you can look at it from other direction. Whoops, again, I've done it from the Z direction or the Y direction, and it looks pretty much the same. So that's a neat little thing to do. And all I've done there is set this slider up, and if I get the settings there, you will see that I actually set it up to go in steps, okay, 0.0625, so that I go up in eighths and quarters and so forth and so on as I go around. So that's actually going to stop at each sort of axis as it comes round, so that I can show the kids what's going on. As I said, particularly if I'm looking from that X direction, then we can get the rotation and see what's happening there as we build our solid. So having demonstrated how I think that's pretty cool, we better show you how, in fact, you can build that. And as we said, that slider is going from 0 to 1. It's controlling the rotation, which is our parameter u. And so all that we do in our function is we change our function. So instead of cos u, we have cos u times turn. And so when turn is 0, we've got no u in there, and so we're back in the xy plane. And as we go through and change the values of turn up to 1, then we get all the values of u and we get our complete rotation. You can do the same thing for rotation around the y-axis, and in this case I called my parameter ROT for rotation, and if we're rotating around the y-axis, let's have a look along the x-axis and see what happens then if we rotate it that way and move this around. So we're rotating around the y-axis, or the did it twice, sorry. Look along the z-axis and you can see what's happening there as we build this thing and it rotates. Or if we look down on it from above the y-axis, then we can see our rotation taking place around the y-axis. So that's something that you can experiment with yourselves, and I think it's a neat sort of thing that even younger students that as soon as they're competent with graphing functions and they've done some trigonometry, it would actually be a neat way to or to use as an application of your periodic functions to build those solids of revolution. So let's go back and just summarize what we've done there, if I can get this to work, and go back to that. So that's around the y-axis, the area between two curves, adjust the parameters to define the region of overlap, and do that with the parameter t, and then rotate both curves using the parameter u, and you've got your region of overlap. And the final thing that I wanted to mention briefly, Brian alluded to it at the start, and that's the idea of 3D printing. If I could create my fantastic wine glass, then to be able to print it and have a physical object like that I could show the kids, or that they could show me if they've done it, I think would be fantastic, but I haven't quite got there yet. But I have got a little photo there of a whole series of curves that are teacher generated from the 1/x curve, and you can see another photo there that a teacher's used 3D printing to print the solid of revolution, and then a series of shells to illustrate to the students how you can build up the volume by summation. So yeah, I think there's huge potential for mathematics to visualize things in 3D. The cost of 3D printers is decreasing. The school that I worked up until recently, before moving over to QUT, has now got 3 of them. And there is an open scripting language that I believe, well, I do because I've got it running. It's called OpenSCAD, but I just haven't mastered the syntax of that yet to be able to create it. But once you create it in a package like OpenSCAD, you're essentially seeing the image in the same way that we saw on the Nspire, created with the parametric functions, and then the SCAD software has the ability to export to what I think there is an STL file or something like that, which is what any 3D printer will be able to read and hopefully print your object. So Peter, if you would like to grab back the control, that's the end of my little session there, and I'll hand back to you.
Thanks very much, Jim, and also thank you, Brian. There's been a lot of love for you in the chat window. This has been a terrific webinar. We've certainly learned a lot about this part of Nspire, which I suspect has been underutilised because of our lack of knowledge. So thanks very much for illuminating us. Brian, thanks very much for showing us an application of transformations and also parametric equations, and also Jim for showing us, you know, a link between two-dimensional and three-dimensional representation of functions and being able to visualize a volume of solid of revolution, and the wine glass activity looks like an absolute ripper. So thanks very much on behalf of all of us to Jim and Brian for enlightening us. This webinar will be available on demand for you to have a look at again and to help with making some of these ingenious files. Jim also, in his PowerPoint presentation, provided a Dropbox link for those TNS files. So without further ado, I'd just like to thank Jim and Brian very much again. Thanks very much to the attendees for listening to this terrific webinar, and everybody have a good evening. So thank you and goodbye.
Thanks, everyone. All good.
Thanks, Peter. Thanks, everybody.